Hi everyone, my name is Daniel, and together with my colleague Dr. Khan, we've developed Trusted Code, which is a framework that evaluates how well large language models can help us create verified and trustworthy code. So, today I'll show you how we're bridging the gap between AI generated code and formal verification to ensure software reliability. So, 41% of all program code globally is now AI generated. But we have a problem. This code is inherently untrusted and it can't be used reliably in critical applications. So, formal verification can establish trust by proving the code's correctness, but it requires lots of manual effort. Our goal with trusted code is to automate this process by identifying exactly what large language models can and can't do. So when we're translating Python code into formally verified specifications, we want to find the capability gaps. So let me walk you through how trusted code works. So first, we take a Python program and we feed it to an LLM. In our case, it's Claude Sonnet 4 by Anthropic. The LLM adds some type annotations in the Python code and it creates a well-typed Python code. Next, the LLM translates this into YML. YML is a specification language that's used by the Y3 verification framework. This is where things kind of get interesting. So we send the Y3 code to Y3's YML code to Y3's prover, and if it verifies successfully, great, we have trusted code. But often what happens is errors occur. So when they do, our system doesn't really give up. So using LangGraph, we've built an iterative repair loop. The error messages, along with the original code and failed Y3 specification, goes back to the LLM. The LLM then analyzes these errors using explicit reasoning, so what we like to call chain of thought prompting, and it then generates a corrected version. This cycle continues for up to 10 attempts. The main thing with this system is that the LLM learns from each error, so it builds a history in a state that helps make it better corrections in subsequent steps. So to understand where the LLMs are struggling, we developed a comprehensive classification system. We have 12 capability gap categories. These fall into three main areas. So first we have knowledge gaps, like when the LLM doesn't understand Y3's library system or how to properly use its APIs. The second are syntactic gaps, where the LLM confuses Python syntax with YML syntax, like when using, for example, Python's division operator incorrectly with Y3, so it uses mod. Third are semantic and typing gaps, where the LLM misunderstands the meaning of data types or how to translate between Python and YML types. So let me now demonstrate this framework in action. So we have our Python function, which is a basic absolute value implementation. It takes a number and returns its positive value. What we do now is we run the main.py with absolute value, absolute_value.py, and we let the LLM do its magic. So watch as trusted code processes it. First, it adds type annotations. Notice it's using float type for the input and output, which makes sense. Then it translates to YML. The LLM is adding the specification. Then it runs the Y3 prover. We get an error, as can be seen here. The error shows unbound function or predicate symbol, and this is kind of an knowledge gap classification error. So that's how we classify it as an environmental knowledge. Then it goes through the self-correction process. So it takes the previous code, it develops an action plan, and based on that, on the second attempt, we get success. So as you can see here, we can see that the prover result is valid. What's fascinating here is that even in this trivial function, it reveals a fundamental gap in the LLM's knowledge of Y3's ecosystem. It didn't know which libraries to use or how Y3 handles numbers differently from integers. We can go further into this by its output. So it will give us all of the output and it will show us the error. So this is an error classified by the LLM. But we also undertake manual error classification. So after testing trusted code on 10 Python programs of varying complexity, we discovered a few important patterns. So the first thing we found is about half of all errors were knowledge gaps, exactly what you just saw with absolute value. The LLM just didn't know enough about Y3's ecosystem and libraries. Next, we found out that there's no linear relationship between code complexity and verification difficulty. Our absolute value function is mathematically simple, yet it required correction, but some more complex functions, like for example the factorial recursive, succeeded on the first try. Third, we found out that when faced with complex specifications, the LLMs tend to give up and revert to simpler postconditions. This was a behavior we observed in our bubble sort algorithm. Trusted code represents a significant step forward for automated formal verification. By identifying these capability gaps through systematic analysis, we are hoping to pave the way for better LLM training and prompting strategies. Our framework is open source and it's available on GitHub. We believe that as LLMs improve their understanding of formal verification frameworks, we'll see a future where AI generated code can automatically be proven correct, which will lead to software being more reliable and trustworthy. Thank you very much, and goodbye.